Okay, so this is the notes video for 5.5 and 5.6, which is our last section of this chapter. Remember, your test is on Friday, and Wednesday we'll have a review day. If you have any questions, you can always email me, but we'll go over questions on Wednesday as well. So the first thing I put is just the identities from last class, our angle, sum, and difference identities. And then for our new section, we're going to start with reviewing some of our triangle congruence theorems from geometry. So remember, in geometry we talked about having theorems that we can use in order to prove that two triangles are congruent, and we were actually going to use those in talking about the laws of sine and cosines. So our triangle congruence theorems, we have ASA when we're given two angles and the side between them. We have AAS when we're given two angles and a side that's not between them. SAS if we have two sides and the angle between them. And then we have SSS if we have all three sides. We do not have congruence theorems for let's do SSA when I have two sides and the angle that's not between them. And we also do not have a congruence theorem for AAA. We can have a similarity theorem for AAA, but not congruence. Okay, we also need to recall that the angles of a triangle always add up to 180 degrees. So if I add up all three angles of a triangle, they should always add up to 180 degrees, which is pi radians. Okay. In order to talk about the law of sines and cosines, we're going to quickly run through our multiple angle identities. These are ones that I don't expect you to memorize for the test. Okay, so these are the only ones that you don't have to memorize, don't need to memorize for the test. If you need one of these identities, I will give it to you. Okay, so starting with our double angle identities. Our double angle identities is what happens if we let u equal v for our angle sum identities. So for example, if I let sine of u plus u, then we would have equal to sine of u times cosine of u plus cosine of u times sine of u. And now these two terms are actually the same because of the commutative property of multiplication. So then we get that the sine of 2u equals 2 times sine of u times cosine of u. The same way we can derive cosine of 2u and tangent of 2u. Notice the first identity for cosine of 2u, we can use the first Pythagorean identity to substitute for cosine squared u or for sine squared u, and that's where these other two come from. And this identity is actually missing a 2 right here. So if you can add that into your notes, please. It should be 1 minus 2 times sine squared u. And then if we solve for cosine squared u or for sine squared u, we end up with what we call the power reducing identities. So this takes sine squared and writes it as cosine of 2u. So we would go from a quadratic or a second degree down to a linear or a first degree. We can do that with cosine, and then if we divide sine divided by cosine, we'll get tangent squared u. Okay. Similarly, our half angle identities come from our power reducing identities if we take the square root of both sides, which means we need a plus or minus. And then instead of u, we substitute u over 2. And those are called the half angle identities. So all of these multiple angle identities, the double angle, the power reducing, and the half angle identities, come from our angle sum and angle difference identities, which we proved last class. How do we use these? In example 1, we want to solve algebraically on the interval from 0 to 2 pi that sine of 2x equals cosine of x. Well, the first thing we need to do is write these all in terms of the same trigonometric function, or look at how we can simplify this in order to solve for x. So what I'm going to do is I'm going to say, well, sine of 2x, I can rewrite sine of 2x using my double angle identity. So I'm going to say, and now this is not a proof, we need to solve for x. So this one we can manipulate both sides of the equation. So sine of 2x equals cosine of x, and I want to solve, so I'm going to rewrite sine of 2x as 2 times sine of x times cosine of x. And then I'm going to subtract minus cosine of x equals 0 because I know I want to solve for x, so I want all of the x's on the same side of the equation. Factoring out cosine of x, I'm left with 2 times sine of x minus 1 equals 0. Using the zero product property, I get that cosine of x equals 0 and 2 times sine of x equals 1. So let's start with when is cosine of x 0. Cosine of x is 0. X is 0 here and here. So x is pi over 2 and 3 pi over 2. And we're only looking between 0 and 2 pi, so I don't have to find coterminal angles. Divide by 2. When is sine of x 1/2? When my y value is 1/2, I'm at pi over 6 and 5 pi over 6. And then we need to check for any extraneous. Well, I don't have any tangents, I don't have any reciprocal functions, so we know that the denominators are okay, which means that all 4 of these are my solutions. So x equals, you don't have to put them smallest to largest, but I like to. So pi over 6, pi over 2, 5 pi over 6, 3 pi over 2. And that will be my solution. If I had any reciprocal or quotient functions in here, so tangent, cotangent, secant, cosecant, then I have to double check and make sure that these don't give me any zeros in any denominators. Let's look at example 2. Alright, so in example 2, I notice this is a half-angle identity. Remember, our half-angle identities came from the power-reducing identities. So if I'm looking at this, this is squared and a half-angle. So instead of taking the square root and substituting the half angle, I'm just going to substitute the half angle into the power reducing identity. So we have sine squared x equals 2 times my identity for sine squared, but I'm replacing u with x over 2. So 1 minus cosine of 2 times x over 2 is just x over 2. Okay, and then the 2's will cancel, and now I have 1 minus cosine of x, which looks very familiar. It's very similar to our Pythagorean identity, so let's go ahead and substitute the left side with the Pythagorean identity. 1 minus cosine squared x equals 1 minus cosine of x. Now I can manipulate both sides of the equation because, again, this is not a proof. And then I want to get all of my x's to one side, so I'll do plus 1 plus cosine, minus 1 plus cosine squared x minus 1 plus cosine squared x. 0 equals cosine squared x minus cosine of x, which I can then factor. I can use the zero product property. And then we look at the unit circle. So when is cosine of x 0? Here and here. Pi over 2, 3 pi over 2. When is cosine of x 1? Well, x is 1 only here, which is 0. And then all of these, I'm looking for all of the angles, not just on an interval, so I want to write these as their coterminal angles. Well, because these are half of a rotation apart, I know I can write this as pi over 2 plus pi n. And this I can say plus 2 pi n. So I have that x equals the set of pi over 2 plus pi n, comma, 2 pi n. Simplifying 0 plus 2 pi n is just 2 pi n. There we go. All right, let's take a look at the next page. The law of sines is one of the most important theorems that we're covering this chapter, which means that it's really, really important and you should definitely know how to apply it. It's relatively simple to set up. So in any triangle, we can say that the angles and opposite sides give us this ratio where sine of the angle divided by sine of the side equals each ratio of sine of the angle divided by the side. So sine of A divided by A, sine of B divided by B, sine of C divided by C. If I'm looking for B, then I'll use B with one of the other ratios that I know both parts of. Okay, Now we can apply this to any triangle, which is really useful, not just a right triangle. And the reason we can do that is because we use the altitude of any triangle. Remember, the altitude is the height drawn as a perpendicular to any side. And the way that we can set this up is by drawing that altitude for any given triangle. It doesn't have to be a right triangle. And if we look at sine of angle A, at the right triangle formed by the altitude, sine is opposite over hypotenuse, so it's h over b, okay? And then we can multiply both sides by b so that we get b times sine of a equals h, which means that we can set that same thing up for angle b. This right triangle here is opposite over hypotenuse, so h over a, multiply both sides by a, okay? And since h equals h, the height of this triangle is the same as itself, that's the reflexive property, we can set up that b times sine of a equals a times sine of b, and then solving that for the proportion. So using all of those properties from geometry and trigonometry together to get this of sines. Okay, now if we draw our altitude on another side, we can set up this same exact process to see the proportion with the sine of c divided by c. So we get this ratio for all three sides and angles of the triangle. Let's go ahead and apply it. All right, so how can we apply the law of sines? Any triangle where we are given two of the angles, we can use the law of sines. So that's our case of AAS and ASA. And the reason this works is because if I have two angles, I automatically know the third because the sum of any three angles of the triangle is 180 degrees. So I can draw a triangle, and I can say here's A, B, C. Across from angle A is side A, B, C. Angle A is 36 degrees. Angle B is 48 degrees. Angle C is going to be 180 minus 36 minus 48, which is 96 degrees. So angle C is 96 degrees. We also have that side A is 8. So we need to find sides B and C. So we want to set up a proportion where, let's find B first. Now, because the proportion is equivalence of ratios, I can also write this as A divided by sine of A equals B divided by sine of B equals C divided by sine of C. So if I'm solving for a side length, setting it up this way might be easier because then instead of having to cross multiply and then divide, I can just multiply by the denominator. I'll show you what I mean. In example 1, we want to solve for B. So if I set A over sine of A equals B over sine of B, I know A is 8 divided by sine of 36 degrees, make sure you're in degree mode, equals B divided by sine of 48 degrees. I can multiply both sides by sine of 48 degrees. Sine of 48 degrees and have B. Whereas if B was in the denominator, I would have to multiply B and then divide by this whole fraction in order to isolate B. So we get that B equals sine of 48 degrees times 8 divided by sine of 36 degrees. Into the calculator it goes, and we end up with 10.11. Now this is not an angle, this is a side length, so this is whatever units of the side length, not degrees. 10.11. We're going to do the same thing for side C. So I'm going to use A divided by sine of A equals C divided by sine of C. Now the reason I'm choosing to use the ratio with A's instead of B is because we had to round B. So to get the most exact answer, we'll use what was already given to us that we know exactly. So 8 divided by sine of 36 degrees equals C divided by sine of 96 degrees. Multiply both sides by sine of 96 degrees. into the calculator equals 13.54. Again, this is not an angle, it's a length, so that's our answer. Okay, we can label it onto the triangle. 10.11, 13.54. Notice, just like we saw in geometry, the shortest side is across from the shortest degree, the smallest angle. Smallest angle is smallest side. Smallest angle, middle side, largest angle, largest side. And then we have our ambiguous case. So what does it mean to be an ambiguous case? Let's look down here. What happens is, for the ambiguous case, if we're not given two angles, we're only given one angle. Remember, this was not a congruence theorem, SSA, which means that there's other possible triangles that could be created. So what happens is, if I have an obtuse angle, and I'm given a side and an angle, and another side. So let's call this the first side, and here's my given angle, and side 1. Okay, then if angle is greater than 90, so it's an obtuse angle, then I know that side 2 has to be greater than side 1. Why is that? Well, if side 2 is smaller, then it will never intersect the third side of the triangle. So think about if side 2 is too small, it'll never intersect the third side of the triangle here. So the second side has to be longer than the first side. So BC has to be longer than AB in this example here to create a side AC. Okay, now what happens if my angle is acute? Well, here I'm given an acute angle, and here's side 1. And what happens is, if side 2 is shorter than side 1, now instead of not being able to intersect my third side of the triangle, there's the possibility that there will be two places that we can intersect. So let's say this is how long my side is. And notice there are two possible triangles here, two places for point C to be. So if side 2 is smaller than side 1, I can have two possible triangles. Okay, now if side 2 is smaller than h, which is the distance between B and this side, the side length that we don't know, then there's no possible triangles. So if side 2 is smaller than h, which is the altitude, 0 possible triangles. Okay, so sometimes we have one triangle, sometimes we have two triangles, sometimes we have 0 triangles. There's an activity here that you can explore on your own. You can do it right now during class, you can do it at home, that lets you see and interact with these cases. Okay, but let's look at an example. In example 3, we want to solve triangle ABC, given that side A is 7, side B is 6, and our angle is 26.3. So angle A does not touch side A. That's an important thing to notice here. So the first thing I'm going to do is I'm going to draw my angle. All right, so here's an angle that's approximately 26.3 degrees. We know this is angle A, so we can label here side B. Now side B is the side length that we know, so let's label it here maybe. Here's side B, which makes this point C. Okay, side A is 7, B is 6, A is 7, so A is longer than side B, which means that it could intersect here. Now that's not a perfect circle, but it's kind of a visual of how do I know where side A will intersect. Well, if I took a piece of string that was 7 units long, I could swing it around and it will intersect the line over here. And that is point B. And the distance between A and B is side C, and the distance between C and B is side A, which is 7. So this is side C, and this is side A, which is 7. Okay, and we need to find side C, and we need to find these other two angles. So I know that a triangle is possible. I know that this is the only place point B could be because it doesn't intersect this kind of ray that we created from the angle anywhere else. So let's use the law of sines. I have angle A and side A, and we're looking, let's find angle B first. So let's say sine of A divided by A equals, sine of B is our unknown, divided by B is 6. We actually know angle A, so let's put in that angle measurement is 26.3 degrees. Okay, so to find sine of B, multiply by 6, multiply by 6, multiply by 6. 6 times sine of 26.3 degrees divided by 7 equals sine of B. So to get B by itself, I need to use sine inverse. So now I will get B equals sine inverse of 6 times sine of 26.3 degrees divided by 7. Again, making sure that our calculator is in degree mode. Punch this into the calculator and you'll get that B equals 22.3 degrees. Now we need to do the same thing for C, okay? But for C, we don't have the side length or the angle. So now that we have angle B, 22.3, we can calculate angle C by 180 minus 26.3 minus 22.3. So angle C is 131.4 degrees. So angle C, maybe I'll mark it like this, angle C equals 131.4 degrees. Now if it's the capital letter, you know that we're talking about the angle, but since C is hard to tell whether it's capital or not, if it's not written in a line that has other letters, I like to mark it as the angle just so I can tell that that's my capital C. Now we need to find side C, lowercase c, so we can set up, again, I'm going to use A as my starting ratio because I know both things from A in the given problem. So to find side C, I'm going to start with side A on top, divided by sine of 26.3 angle A, equals side C divided by sine of angle C, which is 131.4 degrees. So C equals sine of 131.4 degrees times 7 divided by sine of 26.3 degrees, which means that side C equals, into the calculator, make sure you're in degree mode, 11.85. And those are our missing pieces. Okay. So for law of sines is when I have two angles given, I know exactly the triangle that will be given. If only one angle is given, then I have to construct my triangle carefully and make sure that it's possible. 1 case, 0 cases, 2 cases. Let's look at example 4. All right, so in example 4, again, we are given only one angle, which means we have to construct our triangle very carefully. So we'll start by drawing the angle that we're given, which is angle A. Now, I draw this bottom line long because I don't know where this side is going to intersect my angle. I know that this side here, I can call that side B, which means this is AC, which is 7. And then I know that side A, which extends from point C, is 6 units long. So again, I'm going to draw my kind of sort of circle. So point B could be here or here. If I have a side length of 6, it's this long, which means it has 2 possible points of intersection on my triangle, which means I have 2 possible triangles here and here, 6 and 6 for A. Notice this is an isosceles triangle, and we're going to use that fact in solving for both triangles. The easiest thing to do here is to first solve for the acute angle, the acute triangle where A and B are both acute. So the reason that it's easier to do that is because our inverse functions will always give you the acute angle. And then we can use the idea that these are isosceles, so this angle is supplementary to this angle, to find the obtuse case for angle B. So let's start by looking at this triangle with acute angle B. So this is A, C, B, where B is acute. Angle A is 30 degrees. Side B is 7. Side A is 6. Not drawn to scale. Okay, and we need side angle B, side and angle C. So let's do angle B first. So sine of 30 divided by 6 equals sine of B divided by 7. So B equals sine inverse of multiplied by 7. 7 times sine of 30 divided by 6. B equals, into the calculator, make sure that you are in degree mode, and we find that angle B is 35.7 degrees. Okay, so this is for triangle 1. I'm going to put a line. We'll use the other side for the second triangle. Then to find angle C is 180 minus 35.7 minus 30. We find that angle C is 114.3 degrees. And then finally side C. So we're going to use the side that we were given both pieces of information for, which is A. 6 divided by sine of 30 equals C divided by sine of 114.3. Sine of 114.3 degrees. So C equals, into the calculator in degree mode, C is 10.94. Okay, and this is for the triangle with acute angle B. Acute. To find the triangle now with obtuse angle B, something like this, BAC 37.6. Now remember, these two angles were supplementary, so to find angle B, we can take 180 minus the angle that's congruent, which is 35.7 degrees. So we find that angle B, which is 144.3 degrees. To find angle C, we do 180 minus 144.3 minus 30. So we get angle C is tiny, 5.7 degrees. We would expect it to be very acute because it's a very small angle in our diagram. And then side C finally, so we have side A, which is 6, divided by sine of angle A equals side C. Side A is 6. Side C divided by sine of angle C, which is 5.7. So C equals sine of 5.7 times 6 divided by sine of 30 into the calculator, and we get that C equals 1.19. And here are our final measurements for the obtuse case. All right, so that's the law of sines. Now we're going to take a look at the law of cosines. The law of cosines should look a little bit familiar because it's also called the generalized Pythagorean theorem, which means it's very, very similar to the Pythagorean theorem, except that it can be used for any triangle. So if you'll remember how we found the sum and difference formulas last class, we can construct the law of cosines using a similar method, and we can find that a squared equals b squared plus c squared minus 2bc cosine of a. Okay, so notice the side length that we're looking for is the angle that we use, and then we have the other two side lengths, the sum of their squares, minus 2 times those two side lengths. Okay, so we can set this up for any of our 3 side lengths. If I look at this last one, c squared equals a squared plus b squared, it's the Pythagorean theorem, except minus 2ab cosine of c, which when I have a 90-degree angle, this whole thing is 0, and therefore it's just the Pythagorean theorem. Okay, so the way to remember the law of cosines is start with the Pythagorean theorem, minus 2 times the sides that I have times the cosine of the angle that I have. And that will give you the side that you are missing. Okay, so think about the law of sines. We had to have one completed ratio where we had the side and angle of the same variable. The law of cosines is when I have one piece of information from each of the variables and only one of them is an angle. If I had 2 angles, I can use law of sines, but for one angle and then sides that don't match that angle's variable, we use the law of cosines. Let's look at an example. In example 5, we're looking at triangle ABC, given that I have side A, side B, and angle C. I have all 3 variables here, A, B, and C, and only one angle, so that tells me I have to use the law of cosines. The first thing we're going to solve for is the missing side. So c squared equals a squared plus b squared minus 2ab times cosine of c. The side that we're looking for, c squared equals the sides that we know, 11 squared plus 5 squared minus 2 times what we know, 11 times 5 times cosine of 20 degrees. As soon as I write that degree sign, I should remember to put my calculator in degree mode. I keep saying that, even though so far all of our examples have been in degree mode, because it's something that you should be mentally checking every time you do calculations in your calculator. So this is 121 plus 25 minus 110 times cosine of 20 degrees, which is c squared. So then c equals the square root of 146 minus 110 times cosine of 20 degrees. All of that goes into the calculator. We get c equals the square root, and you can do that all as one step, 42.63. So c is 6.53. This is not an angle, it's a side length, so that is our value. Okay, so now I have all 3 sides, and I need 2 angles. And to find the missing angles, we're going to still use the law of cosines. The reason we do that is because that will use the inverse functions and automatically make sure that we are all using the same triangle. Okay, so again, we're using the law of cosine, but now we want to find angle A, for example. So if I want to find angle A, then I want to use the side that uses side A. So a squared equals b squared plus c squared minus 2bc cosine of angle A. And now this is going to be our unknown. We know everything else. 11 squared equals 5 squared plus 6.53 squared minus 2 times 5 times 6.53 times cosine of A. 121 equals 25 plus 42.63 minus 65.3 times cosine of A. The way I multiplied that is 2 times 5 is 10, so we're just moving the decimal place once. And then we want to subtract everything over, so 121 minus 25 minus 42.63 equals negative 65.3 times cosine of A. Divide by negative 65.3, and then take cosine inverse. So we get that A equals cosine inverse of all of this. It's inverse, so I should end up with an angle, and you should get 144.80 degrees. To find our last remaining angle, so we have angle C and angle A, so to find angle B, we have 180 minus 20 minus 144.80, which gives us 15.20 degrees. To find a third angle, you'll never need to use a law of sine or cosine. We can always just use that angle sum theorem, that the sum of all of the angles of a triangle is 180 degrees. Okay, so notice this second part that we did is the same as what we would do, is the same process as what we would do if we were given all three sides. And that's what we have in example 6. So in example 6, we're looking at the three given sides. A is 9, B is 7, C is 5. I know I can't use the law of sines or any of our other theorems because I have just the three sides and no angles. And so we have to use the law of cosines. The law of cosines, now it doesn't matter if I solve for angle A, B, or C first, so you can choose, okay? So I want you to try pausing the video and doing this with your group, and then resume the video and we'll go over the answer together. Okay, now again, it doesn't matter which angle you solve for first. I like to go in alphabetical order, so I'll choose to solve for angle A first. A squared equals B squared plus C squared minus 2 times the ones that are on the right side of the equation, BC, times cosine of the one on the left side, which is capital A. Okay, substituting in, 9 squared is 81 equals B squared is 49 plus C squared is 25 minus 2 times 7 times 5 times cosine of A. So 81 minus 49 minus 25 equals negative 70 cosine of A. Divide by negative 70. So then we have 81 minus 49 minus 25 divided by negative 70, negative 1 over 10, and then we do cosine inverse, so A equals cosine inverse of negative 1 over 10, and we should get, and now if you're in degree mode, it'll give you your answer in degrees. If you're in radian mode, it will give you your answer in radians. I didn't specify here, so either one would be acceptable. I'm going to go ahead and give the answer in degrees because degrees tend to be what we understand a little bit better because we've been using them for longer. So the measure of angle A is 95.74 degrees. However, we know that to convert that to radians, we would multiply by pi and divide by 180, and then you can write your answer in radians as well, and it'll be equivalent. Okay, now we're going to look for part B. Again, angle B, so I want to use the law of cosines. So we have B squared equals A squared plus C squared minus 2 times AC times cosine of angle B. Substituting in everything we know, 49 equals 81 plus 25 minus 2 times 9 times 5 times cosine of B. 49 minus 81 minus 25 equals negative 90 cosine of B. Divide by negative 90. Divide by negative 90. Into the calculator, we get 57 over 90 equals cosine inverse. So cosine inverse of this. And we get that angle B equals, again, I'm going to give it in degrees, but you can always find the equivalent in radians. 50.70 degrees. I have two angles, so to find the third angle, we subtract from 180 minus 95.74 minus 50.70 into the calculator, and you should get 33.56 degrees. So there are our three angles. Okay, finally, the last problem, and this is, it doesn't have an example number, but we could call it example 7. Okay, this is an application. So we have a forest ranger, Christina, at ranger station A, and she sees a fire in the direction 32 degrees east of north. I'm going to do a little compass, never eat soggy waffles. Okay, so east of north means I start at north and I go towards east by 32 degrees. So she's at ranger station A. Here would be north. I go 32 degrees east, and here's the fire. Okay, Ranger Rachel at Ranger Station B, 10 miles due east. Here we go, 10 miles due east is Ranger Station B of A, sights the same fire at a line 48 degrees west of north. So again, we start with north, and then we go to the west by 48 degrees. Find the distance from each ranger station to the fire. So we want to find B and A. Okay, now B is going to be the distance from the fire to ranger station A. So be careful with how you define your variables, okay? Now I want to find in this triangle, if I know that there's 32 degrees is complementary, right? Because north to east is a 90-degree angle. So 90 minus 32 is 58 degrees. And then the same over here. From north to west is a 90-degree angle, so complementary to our given angle is angle B, which is 42 degrees. Okay, so I have two angles. I can always find the third. Our third angle here would be 180 minus 58 minus 42, and that gives us 80 degrees. So now we have distance C and side C, we can use the law of sines. Once I have that ratio, I know I can use the law of sines. If I don't have a ratio with both pieces, then I have to use the law of cosines. But since I have both pieces, I can use the law of sines. Let's solve for A first. So A divided by sine of 58 degrees equals C divided by sine of 80 degrees. Then A equals 10 times sine of 58 degrees divided by sine of 80 degrees. And distance A equals 8.6. I know the units, so let's put it miles. Then we do the same thing for B. B divided by sine of 42 degrees equals 10 divided by sine of 80 degrees. B equals 10 times sine of 42 degrees divided by sine of 80 degrees. B equals into the calculator. We happen to get 6.8 miles. But because we know the situation, we should answer as a statement back to the question. So the question was, how far away are each ranger station? So ranger station A is distance B. So 6.8 miles from the fire, and station B is 8.6 miles from the fire. Okay, so it's nice that we finally have a direct application of one of our theorems. Remember, next class is a review class, and then we have the test on Friday. So if you have questions, you can always email me, or you can come into office hours anytime this week.